Hello, I'm Professor Lucht of the University of Rhode Island. I'm also the Associate Editor of the Journal of the Electrochemical Society. And today I'd like to give the first of a series of presentations on my research and an overview of the general aspects of lithium-ion batteries. So the first lecture today will be primarily an overview of lithium-ion batteries. And then the following lectures will focus on electrolyte first, and then aspects of my research on the electrolyte interfacial reactions with the anode of the lithium-ion battery, and then finally on the electrolyte interactions with the cathode of lithium-ion batteries. So with that, we'll go on to the, let me first, share my screen. I apologize, there we go. Share. And so once again, my name is Professor Brett Lucht, and I'm at the University of Rhode Island, and it's a privilege to be giving these series of lectures at Kyoto University. So first off, I'd like to start off with the general aspects of lithium-ion batteries. As you all know, lithium-ion batteries are a critical component of our society today. The lithium-ion batteries power many of the electrochemical devices that we all use all the time, such as laptop computers and cell phones. And more recently, lithium-ion batteries have started to become widely used in power tools and also in electric vehicles, and also in grid scale storage units, which are important for renewable energy systems. So we're going to go over kind of many of the basics of these materials. And once again, the lithium-ion battery packs that are actually in, or battery cells that are actually in your component, in your devices, look something like this. This is a similar battery pack that's used for most cell phones, or similar packs are used for laptop computers. The lithium-ion battery packs, which are used for electric vehicles, are much larger, such as this, and usually the entire base or the bottom of the vehicle. So why, there's basically a big interest in electrical vehicles, in the use of electric vehicles. A lot of this has to do to the concerns on the planet associated with the climate change and global warming, and the fact that there's a large percentage of CO2 emissions result from vehicles that burn gasoline or petrol. And these are a significant problem. And basically, there's a big interest in expanding lithium batteries from primarily being used for consumer electronics devices into the larger applications such as electric vehicles, and as I said, also in grid scale storage. So what you've seen here in the last decade or so is the demand, gigawatt hour demand of lithium-ion battery production has steadily increased from 2010 through 2020. And at the same point, the price of the production of these materials, of these batteries, has significantly decreased. There are several reasons that the price has decreased. One is the materials which are in the battery have decreased in cost, which we'll go over later on in this lecture. And then also, there's been a significant decrease in the overall production cost of these batteries. Basically, the battery manufacturing companies have become much more efficient about their manufacturing processes. And also at the same time, as the scale of production has increased, basically the price has steadily decreased just because of the volume of these materials being generated. So, why lithium ion? I mean, this is always a frequent question as to why the lithium ion batteries are the batteries that are so widely utilized in both consumer electronics devices and also in electric vehicles. And there's a few reasons for this. So first off, if you look at the standard potential table for standard chemicals on the periodic chart, what you can see is that lithium is the strongest reducing agent. It's that is present on the periodic chart, and so basically you don't have any options of materials with a lower potential than lithium metal. And then at the same point, the materials that are utilized for the cathode materials have production potentials that are close to that of oxygen and or fluorine, which are very, very high oxidation potentials within these materials. And so basically what you have is an electrochemical potential between the anode and the cathode of basically as high as one can obtain with the elements that we have at our disposal on the periodic chart. So at the same point, if you compare lithium ion batteries to other traditional rechargeable batteries, such as the lead acid battery or NiCad or nickel metal hydride batteries, the lithium ion battery has both a greater energy density, gravimetric energy density, and also a greater volumetric energy density. And so what this means is that basically you can fit the same amount of energy into either a smaller space or into a smaller weight or mass of material. And so basically what you can do is you can power the same kind of device that you would with NiCad or nickel metal hydride with much smaller and lighter battery, which is why lithium ion batteries are so important, is because of this very, very high energy density, which once again, this high energy density is enabled by the very large electrochemical potential window. So we'll start off with our discussion of lithium ion batteries by going a little over the history of the lithium ion battery. And one of the most important aspects of the history of the lithium ion battery was that last year in 2019, the Nobel Prize in Chemistry was awarded for the development of the lithium ion battery. And the Nobel Prize was awarded to three researchers, Professor John Goodenough from the University of Texas at Austin, Professor Stanley Whittingham from the University of Binghamton in New York, and also Dr. Akira Yoshino from the Asahi Kasei Corporation in Japan. And basically they were awarded this, the Nobel Prize for the development of the lithium ion batteries, and of course the very, very large impact that lithium ion batteries have had on all of our lives by enabling the portable power that we all are now very, very dependent upon in terms of our cell phones and laptop computers and tablets, but also in terms of enabling the conversion of vehicles from gas-powered, petroleum-powered vehicles into battery-powered vehicles of the future to address a lot of our environmental concerns. So the initial battery that was first developed by Professor Whittingham utilized titanium disulfide as the cathode material and lithium metal as the anode material. An electrolyte, liquid electrolyte, which allowed the lithium ions to go back and forth between the cathode and the anode. Now, what was really novel about this discovery by Professor Whittingham was that basically this titanium disulfide material was a layered compound with spaces between the layers, which allowed the lithium ions to intercalate into these spaces between the layers of the titanium disulfide. And so this general concept of using an intercalation compound such as titanium disulfide as an electrode material for a battery was a new concept that basically was discovered by Professor Whittingham in relationship to the intercalation of these lithium ions into the layers. And so this was a really exciting development. And once again, this material was coupled with a lithium metal anode. Some of the problems with this system is, first off, the voltage of this was only 2 volts. Titanium disulfide is not a very high potential cathode material. And then the other problem that we can see is that basically you encountered issues with the generation of whiskers or dendrites from the lithium metal. And so basically what would happen is as you cycle the battery back and forth, the lithium would start to be deposited on the surface of the metallic lithium, and it would form these dendrites or spires or spikes or whiskers or whatever you want to call them on the surface, and as the battery continued cycling, these whiskers would grow longer and longer and longer until they came in contact with the surface of the cathode material, at which time the battery would short or potentially cause fires or explosions or things. And so this was, of course, due to safety concerns, a no-go in terms of the battery development, because you can't have batteries catching fire and exploding in devices. That's certainly not acceptable. So the next really key development in the lithium-ion battery realm was done by Professor Goodenough. And basically, what he realized was two important things, which was first was that you could utilize lithium cobalt oxide as a cathode material. Now, why is this important? Well, first off, lithium cobalt oxide has a much higher potential, 4 volts, as opposed to the 2 volts for the titanium disulfide. So this is effectively a doubling of the overall potential of the cathode, and overall a doubling of the energy storage potential of the battery. And the other really important thing was that this cathode material could be made or prepared in the lithiated state, which is basically in the charged state effectively. And so basically you can that basically provides the lithium ions in the cathode material already, and can be supplied for additional cycling. So the final key to the development of the lithium-ion battery was really effectively the removal of the lithium metal anode, and this was done by Dr. Yoshino. And what he recognized was that first off, you could use basically polyacetylenes for anode materials within lithium-ion batteries, but then more easily you could use petroleum coke and also graphite as the anode material for lithium-ion batteries. Now, this was really a critical observation, and once again, really very much enabled by Professor Goodenoug's development of lithium cobalt oxide, because up until this point, usually in these battery designs, or these lithium battery designs, the source of lithium which was being cycled back and forth was the lithium metal itself. But since Professor Goodenough developed a cathode material, lithium cobalt oxide, which could be manufactured and the batteries could be prepared with the lithium already present in the cathode, then you could use that lithium to cycle back and forth. What that made was, what enabled it was that you could use an anode material other than lithium metal. And what Dr. Yoshino recognized was that you could use these cokes or carbons or polyacetylenes for the anode material. And so the source of the lithium would be in the lithium cobalt oxide. You'd cycle the battery and the lithium ions would go into the coke or the graphite and then back and forth out. And what this really developed, the primary component of development of this was actually you made a battery that was safe, and which was a critical development, because you no longer had the lithium metal anode, you no longer had the problem with the dendrites growth or the whisker growth, which would then short the battery. And this basically enabled the development of the modern lithium-ion battery. And so with this, we'll just kind of briefly go over all of the components of the modern lithium-ion battery, which once again was the outcome of the research by Doctors Goodenough, Whittingham, and Yoshino. And so with that, basically, the cathode materials that are currently in lithium-ion batteries, most of them are pretty similar to the materials that were originally developed by Professor Goodenough, which is the lithium cobalt oxide. There has been some development of other lithiated metal oxides, which we'll see later, because one of the challenges so there are several challenges with lithium cobalt oxide. First off, the cobalt is a very expensive metal. It's also a relatively toxic metal. And also a lot of the cobalt that is utilized in the world is mined under, we'll say, questionable circumstances in which the mining of the materials occurs. So there's a big push to get away from cobalt on the cathode side. The other issue with the cathode side is that while lithium cobalt oxide, which usually operates at a voltage of about 4.1 volts, versus the graphite anode versus the lithium metal anode, there's a big push to go to higher potential, because basically if you increase the potential of the cathode, you increase the energy density of the battery. And so there's a big push on that. On the anode side, the current lithium ion batteries are predominantly anodes composed of graphite, very similar to the petroleum coke that was originally developed by Professor Yoshino. And basically, as is shown here in the diagram, the lithium metal starts off in the cathode. As you charge the battery, the lithium ions go through the electrolyte and then into the layers of the graphite. The next component of the lithium-ion battery is the electrolyte, which currently is typically lithium hexafluorophosphate, LiPF6, and a mixture of carbonate solvents. But one of the real issues with the electrolyte is that the electrolyte is not stable to the entire electrochemical potential window of the lithium-ion battery. As I said, one of the really great things about the lithium-ion battery is the very large difference in electrochemical potential. Once again, the lithium metal is about -3 volts. -3 volts compared to the saturated hydrogen electrode, while basically the transition metal oxides are roughly 1 volt higher than that, which gives you a 4 to 4.5 volt window. The problem with this is that basically the lithium-ion batteries, the electrolyte isn't stable to this really wide electrochemical potential window. And so what happens is on the anode side, during the first charging cycle of the battery, some of the electrolyte is irreversibly decomposed. This decomposition reaction generates an interfacial film on the surface of the anode, which is referred to as the solid electrolyte interphase. And this solid electrolyte interphase is critical to the overall performance of the lithium-ion battery. Without the generation of this stable solid electrolyte interface on the anode surface, every time you charge the lithium-ion battery, more of the electrolyte would decompose and be consumed, and less of the lithium ions would be able to go back and forth between the two electrodes. So we will spend a significant amount of time in one of the lectures of this series going over the formation mechanisms of this solid electrolyte interface and the stability of it and the importance of it for the development of the current lithium-ion batteries and also for the development of future lithium-ion batteries. So at the same point, as you charge the lithium-ion battery, the potential of the cathode also starts to get relatively high. And as I mentioned, one of the real significant interests in the development of future lithium-ion batteries is to get the cathode to operate at even higher potentials than what is currently used for lithium-ion batteries. And this also results in a problem because now you're starting to get to very high potentials, 4.5 volts versus lithium metal. These are very high potentials, and what you start to have now are oxidation reactions of the electrolyte on the surface of the cathode. Now, once again, these can generate some cathode surface film, as is depicted here, and the generation of this cathode surface film, or at least the generation of a stable cathode surface film, is something that's currently being widely investigated by many researchers in the lithium-ion battery field. And it's something that we will discuss once again in great detail in a further lecture. So let's go back to just kind of the battery basics here. So, when you're building a battery, a lithium-ion battery, the lithium-ion battery is typically constructed of multiple lithium-ion cells. And so earlier in the presentation, I showed you the single lithium-ion battery pack or pouch. And basically what you will take is a whole series, and these are basically examples down here. So these are a whole bunch of individual lithium-ion batteries that are all kind of bundled together to make a pack, a larger electrochemical system. You can you connect these basic lithium-ion cells either in parallel to increase the current, or you can do it in series to increase the voltage. And frequently what is done, especially for electric vehicle applications or grid scale applications, is you get some combination of some of the cells in parallel and some of the cells in series. And basically, you combine these multiple battery cells into this integrated battery module, which is an entire science of its own in terms of the production of these battery packs, also cooling of these battery packs, the design of these battery packs, because many of these things are delivering very, very high levels of current, and also can evolve a significant amount of heat upon charging and discharging. And so basically, these things are very complicated devices. So you can take multiple of these modules and integrate them into one large pack. And just for an example here, the 85 kilowatt hour battery pack, which is in your typical Tesla, contains about 7,104 cells, Panasonic 18650 cells, which we'll see what these are in a minute. But they're basically similar in size to a AA battery. The specific energy, that measures the amount of energy that can be stored and released within the battery, and it can be obtained by multiplying the specific capacity, the amp hours per kilogram, with the battery operating voltage, which we'll see more about in just a second. And so once again, in terms of these lithium-ion cells, there are multiple different types of cells that are currently being investigated or commercially utilized within the market. And the first one is shown here, which is this is a cylindrically wound cell. These cylindrically wound cells are what is used in the Tesla. They're the Panasonic 18650 cells. And in the term 18650, that gives you the measures of the dimensions of the cells. They're 18 millimeters diameter and 65 millimeters long. And then in addition to the cylindrically wound cells, you have the option of basically a coin cell, which most of the research that's done, or a large percentage of the research or initial scale research, is done in these coin cells, which are very easy to prepare in the lab setting. These cylindrically wound cells are not so easily to prepare in a research lab setting, while these coin cells are. The coin cells are also used for smaller devices at times. Although then next, or which I would say the more widely utilized cells are these prismatic cells, which could have metal casings on them, in which usually you have multiple layers of electrodes alternating cathode, anode, cathode, anode, cathode, anode, and then you can kind of wind these things around and pack them into this can, or this prismatic cell. And then finally, which is the more frequently utilized cell currently, are these pouch cells, which basically you take some electrodes, once again, layerings of electrodes with some kind of an aluminum mesh soft pack material. And then you seal these things, heat seal these things around to generate these pouch cells. And so these are just the four most widely utilized cell configurations within the lithium-ion battery space. And while certainly traditionally the cylindrically wound cells have been widely utilized and are currently utilized in Teslas, there's more of a push towards these either prismatic or pouch cells in terms of the larger scale applications, because you can generate basically larger individual cells, and so you would require fewer cells per pack. And as I said here, you may need thousands of these small cylindrically wound cells to make a large electric vehicle battery pack. So once again, we've kind of gone over this, but how does the lithium-ion battery work? So once again, you start off with the lithium in the cathode materials. As you charge the materials, the lithium ions leave the cathode and go into the graphite, and you make lithiated graphite. A point that I didn't make is you typically, especially with lithium cobalt oxide, cannot pull all of the lithium cations out of the cathode material. If you do so, it destroys the structure for some of these cathode materials. And so therefore, you can only pull a limited amount out. And as I said, during the first charge cycle on the surface of the anode, a solid electrolyte interface is generated, an SEI, which passivates the surface of the cathode and enables the overall long-term cycling of the lithium-ion batteries. So continuing on with our battery basics. So first off, in terms of the terminology that's utilized for batteries, there's charge, which is basically an electron or a lithium ion that are being shuttled back and forth, and the unit of this is coulombs. Secondly, there's current, which is a measure of the charge passing a point at a given time. This is typically in amperes or amps. And then in terms of the actual battery terminology, what's most frequently used within the battery community is something that's referred to as an amp hour, which this is the measure of charge passing at a steady current for 1 hour. And so typically with batteries, such as the 1850 cells, there's a rating on the batteries, and the rating is an amp hour rating, is how many amp hours there are in that particular cell. There's also the capacity, which is the amount of charge per unit weight or volume. So usually weight is what you see. And typically you see these either in amp hours per kilogram, or most frequently milliamp hours per gram. And this basically tells you how much potential capacity an electrode material has. And so you hear this term frequently in the terms of referring to either cathodes or anodes, that the electrode material has X milliamp hours per gram, and that tells you, roughly how much capacity that material has. So the cathode capacity, usually the source of the lithium ions is the cathode in current lithium-ion batteries, and this tells you how much lithium it can provide to move back and forth. The anode capacity is how much lithium the anode can hold or accommodate from the cathode. It's an important thing when you build a lithium-ion battery that these two capacities are matched, that they are basically 1-to-1. Or actually usually have a slight excess of the capacity, cathode capacity, and a slight deficiency of the anode capacity, because if you have too much lithium ions in the system, that they will not all go into the anode, you frequently will plate lithium on the surface of the anode, and the plating of the lithium can lead to the same dendrite problems that we saw previously with the lithium metal anodes. And the final piece of terminology is C rate, which the C rate is once again a common term used in terms of how fast you're charging and discharging a battery. And basically what this refers to is the full charge or discharge of a cell in a particular amount of time. So 1C is 1 hour, it takes 1 hour to charge the battery. If you use 10C, it means a very fast charge. It's 1/10 of an hour to charge the whole battery. And C over 10 would be charging very slowly over the course of 10 hours. Now, one of the reasons that battery scientists use the C rate terminology is because the C rate is independent of cell size. So basically, regardless of what cell size is, if you say, oh, I'm charging this cell at 1C, if it could be a tiny cell or a huge cell, it doesn't, 1C is 1C, it takes an hour. So that's why people use it. So in addition, looking at some of the basic battery curves here for lithium-ion batteries. So the top is a simple charging curve, which is the voltage versus capacity. And the bottom one is a simple discharge curve, which once again is voltage versus capacity. And the energy of the battery is equal to the area under the discharge curve. So if you basically integrated this entire area here of the discharge curve, that would give you the overall energy of the battery. Now, the energy of the battery is basically, the voltage times the capacity, which is equivalent to watt hours per kilogram. And so, you usually refer to it as a nominal voltage, which would be like the average voltage here. And then the capacity is simply, once again, the milliamp hours per gram, and usually just simply multiply those two numbers together. But it's not fully accurate, since ideally, you really need the whole integrated area under the curve. Now, with this being said, how can you increase the overall energy density of the lithium-ion battery? Well, of course, if you want to increase the area under this curve, you can either expand either of the two axes. If you increase the voltage, you can increase the y-axis, or if you increase the capacity, you can increase the x-axis. But either way, the way you increase the energy density of the battery is by either increasing the voltage or by increasing the capacity, or a combination of both of the two things. And we'll go over how these types of changes are currently occurring within lithium-ion batteries. Of course, the voltage is, you can only really increase the voltage by increasing the voltage of the cathode material, because basically your lithium metal or your lithiated graphite, which is only about 100 millivolts potential energy above lithium metal, you can't go any lower. And so you're already at the bottom of the window. So the only way you can increase the voltage is by increasing the voltage of the cathode. In terms of the capacity, you can increase the capacity of either the cathode material or the anode material, and we will get to some of these issues as we go forward. So also, another plot that you frequently see within the lithium-ion battery literature is a discharge capacity plot. And so basically, once again, each of these plots, each of these data points is just this point on the curve right here that we previously showed, the discharge capacity. And this shows how the discharge capacity changes slightly as a function of cycle number. And so in this case, we've cycled this battery 400 times, and there's been a slight decrease in the overall capacity of the cell. Now, in this case, the capacity is shown as amp hours, which is, I would say, industrially, what you frequently see is just in terms of full cells, because when you're measuring the amount of current coming out of the cell during charging and discharging, this is the raw number that you effectively get. In addition, you can also show this as milliamp hours per gram for the active material. And so if you take a specific cathode material, such as lithium cobalt oxide, it has a known mass that's on there, and so you can actually report this as milliamp hours per gram, which once again, I would say in the research literature, this is typically what you see, milliamp hours per gram. And then another common one you see is percent capacity retention, and this is really important in terms of cell aging. So if ultimately what you're saying is, well, we built a cell, when the cell is brand new, it has the capacity and the energy that I want, and then how much of this energy and capacity is lost as a function of time upon cycling, or a function of cycling, this is your percent capacity retention. Usually these plots are shown at a constant rate, at a constant charging rate, or a constant C rate, which could be C over 5, C over 2, depending on what type of application, and also a constant voltage. You're charging and discharging from the same, through the same potential window, unless it specifically states it otherwise, that's what you're expecting. Another important analytical technique for lithium-ion batteries is electrochemical impedance spectroscopy. In this technique, what you're doing is varying an AC impedance, an alternating current impedance, and you're basically measuring the lag time between your AC pulses and what's measured on the other side. And by doing so, what you can do is get a measure of the overall impedance or resistance of the cell. And in general, with the impedance spectroscopy, the larger this semicircle is, where the higher the number is here along the x-axis, the higher the impedance of the cell, and more of a problem it is. With these measurements, from my perspective, they're usually kind of relative per the cell, so you need to have direct comparisons of similar cells. But what you can tell is if you make any kind of changes to the battery via the chemistry changes, change in the anode or the cathode or the electrolyte, or changes in the cell that occur over time from aging. You compare, basically a larger semicircle is higher impedance, which is bad. Smaller semicircles are lower impedance, which is preferable. So, kind of summarizing here with what the current lithium-ion battery technology is. So this particular plot shows the history of the lithium-ion battery development as a function of the energy density of the batteries themselves, watt hours per kilogram. From the original Sony development back in the 90s through the Panasonic development of the 18650 cells, where from 1995 through 2015, they steadily increased the overall energy density of these cells. Most of these technology improvements were due to manufacturing processes, where they were getting better and better at manufacturing the cells in terms of making the laminates or the electrodes themselves with higher densities, increasing the voltage slightly of the cathode materials, and optimizing the anode materials also. As in addition, there's other series of materials here where there's the Japan Rising program, the USA Battery 500 program, and also the Roadmap of China program, where all of these different research entities are basically making projections in the future from 2020 and beyond about how much energy density these the batteries will be able to have. As you can see with these much higher energy density batteries, typically you're talking about significantly different chemistry than what is available in the currently lithium-ion battery, such as the Japan Rising program here, where they project a lithium metal anode with a solid state electrolyte, all solid state electrolyte. But here we are currently in 2020, and basically what we have is a series of different cells from different companies, as they can show: SDI, Lyshyn, LG Chem, and Goshen, SK Innovation. And we all have kind of a similar area right here around currently in the 2020 region, where they're at, where we're around 300 watt hours per kilogram for all of these different cell chemistries, similar once again to the Panasonic cell. And what the targets are in the future. However, the majority of this talk, or these series of talks, is really on the current lithium-ion battery chemistry, the one of today, what it has taken to get us here, and we'll have some aspects of what is going on in the future. So it's going back to these current lithium-ion batteries, the ones that are currently in production, from a recent research article published in the Journal of the Electrochemical Society. So as you can see here, this is just an example of the different automotive manufacturers: Tesla, BMW, Nissan, Volkswagen, Toyota, and Honda. And for the different types of battery chemistries that are present in these materials, as you can see, most of them contain carbon as their anode materials, except for Mitsubishi and Honda's with the LTO. And then typically what you have for a cathode material are basically cobalt oxides, or derivatives of cobalt oxides. In this case, this is NCA, which is nickel cobalt aluminum oxide, and this is NMC, which is nickel manganese cobalt oxide. But these are all derivatives of the original lithium cobalt oxide developed by Professor Goodenough. And once again, the graphites are all derivative of the materials that were developed by Dr. Yoshino. And you can see the different battery suppliers for these materials, along with the battery range and the battery packs for this whole series of different batteries that are available. So going on and expanding into the cathode materials that are present for these different lithium-ion batteries. So with some of the advantages and disadvantages. So as we said, lithium cobalt oxide, LCO, is the original cathode material for lithium-ion batteries. For these commercial lithium-ion batteries that have been under production, the midpoint voltage, so this is the average voltage basically, or the median voltage we'll say, for these cells is 3.9 volts, and the specific capacity is 155 milliamp hours per kilogram in these materials, also milliamp hours per gram, same thing. So the advantages of the lithium cobalt oxide, they've got very good cycle life, and they've got very good energy density. Disadvantages, moderately charged, and they don't have the best thermal stability. Although really the biggest problem, which isn't shown here, with the lithium cobalt oxide is the price of cobalt. Cobalt is extremely expensive, and not only is cobalt extremely expensive, it's a rare earth metal, and so the quantity of the cobalt that's available on the planet is not adequate for the development of all the commercial of all electric vehicle applications. And so basically there's just not enough cobalt. So we have to go to something else other than cobalt. It works fine for smaller portable electronics devices, cell phones and laptops. And my understanding is that still a significant number of portable electronic devices currently use lithium cobalt oxide as a cathode material. Another useful cathode material is lithium manganese oxide. Comparable voltage, we'll say. However, this capacity is significantly lower than it is for the lithium cobalt oxide, which is a significant problem with these materials. It's got good thermal stability. It's quite inexpensive because this is just manganese. Manganese is a lot less expensive than cobalt. It's got moderate cycle life, and it's, but it is really very useful for high power applications. So a lot of the power tool applications that we saw earlier, drills and saws and things such as this, many of these will use lithium manganese oxide. NCA and NMC These are two very similar materials, which is nickel cobalt aluminum oxide and nickel manganese cobalt oxide. The NCA cathode is the cathode that is used in the Panasonic cells and for all of the Tesla electric vehicles. This has got very good energy density, good power capability, and good cycle life. All of these things are really good. Disadvantage is it's got moderate thermal stability, and so basically these cells can undergo very high energy processes if they're overcharged. And what you can do is basically they're not as safe as some of the other cells, and so there are safety concerns with both the NCA materials, which have very high nickel content, and also NMC materials with high nickel content, so have similar problems. But this is excellent for automotive power and premium electronic appliances. NMC is basically very similar to NCA. There originally, when NMC was being developed, was a much bigger push towards the NMC materials, mainly because they were considered safer. However, this was with low contents of nickel, which we'll say 1/3 nickel, 1/3 manganese, and 1/3 cobalt. However, in order to get that, when you have this, you have lower capacity. To get the higher and more comparable capacities to the NCA, you have to go to higher nickel contents. And basically, it appears you get similar safety issues with these materials. So these are two similar systems. And then finally, there's lithium iron phosphate, LFP. LFP's got very good thermal stability, very good cycle life, and very good power capability. This is pretty widely used in power tools also. Also, it's used in electric buses in China. The biggest issue with this is the low capacity and the low voltage, which also contributes to the increased stability. Is because this cathode material is a very low voltage cathode material, that's part of why it is stable. However, you really run into problems of the lower energy of these materials. So once again, this is just a simple depiction of the different types of materials that we're going to be going over the next few lectures, and the different, basically the potential or the voltage of the different types of cathode material, and also the capacity of the different both electrode materials, the cathode and the anode. And as you can see with this particular slide, you can see graphite here, which is the common standard electrode material used in lithium-ion batteries. And we have up here lithium cobalt oxide with basically a fairly high potential and still relatively moderate capacity. As you can see, as you go to the lithium nickel cobalt oxides, we get a little bit higher capacities. Lithium iron phosphate, comparable capacity, but lower potential, which is once again one of the problems with it. And so, which is why there's a big push to go to these lithium nickel cobalt oxides. Now on the anode side, graphite's a relatively low capacity material, and lithium metal and silicon are much, much higher capacity materials. So on the anode side, there's a very big push to go to novel, new anode materials, such as lithium metal or silicon, because you have a dramatic increase in the overall capacity of these electrode materials. And on the cathode side, really what you want to do is push higher and higher to potential, and also shift over this way towards higher and higher capacities. So this is just a depiction here of the cathode specific energy for a series of different cathode materials. As I said, lithium cobalt oxide, it is the standard. It's what got us here in terms of lithium-ion batteries. However, unfortunately, the specific energy of the lithium cobalt oxide cathodes is not particularly high. If you go to the NMC, this is nickel cobalt manganese or nickel manganese cobalt, 111. This means the numbers here are ratios, and so this is basically 1/3 nickel, 1/3 manganese, and 1/3 cobalt. We get a slight increase in the specific energy of the cathode material, and also we get a dramatic decrease in the overall cost, because now we only have 1/3 of the material cobalt, and cobalt is by far the most expensive metal. If we compare this to the NCA, which is nickel cobalt aluminum, which usually the NCA materials are 80% nickel, 15% cobalt, and about 5% aluminum. we go to a significantly higher specific capacity for these cathode materials. And as you can see, very similar to the NMC 811, which is 80% nickel, 10% manganese, and 10% cobalt. So really the composition of these two types of materials are relatively similar. They're both 80% nickel, or roughly 80% nickel. And once again, these, as you can see, are very high, significantly higher energy density, specific energy cathode materials than are the NMC and the lithium cobalt. We have various other lithium manganese rich cathode materials, which certainly have the highest specific energy. However, these materials have significant problems, basically both due to cycle life. Really, the cycle life of these materials is relatively poor. And at the same time, there's a voltage fade of the materials, and so the energy fades also. So you have both capacity fade and voltage fade of these materials. And so the biggest problem with these lithium manganese rich materials is the lifetime of the materials is not nearly as high as it is with the NCA and the NCM 811, which these two cathode materials are really currently the two leading cathode materials for high energy density lithium ion batteries. So as we already went over, lithium iron phosphate is a very useful, stable cathode material, relatively low specific energy. Lithium manganese oxide's got slightly higher energy density than lithium iron phosphate, but once again, not a lot higher. Now, one of the other really promising cathode materials is LNMO, which is lithium nickel manganese oxide, which is also referred to as the high voltage spinel. This lithium manganese oxide is typically called lithium manganese spinel. But the high voltage spinel, as you can see, has a significant increase in the specific energy density of compared to lithium manganese oxide, and is, while lower than NCA and NCM, comparable to the NCM 111. And the real advantage, the biggest advantage of this LNMO material is that it's lithium nickel manganese oxide. There's no cobalt in the material at all. And certainly most of the automotive manufacturers are very interested in moving to a cathode material which contains no cobalt, zero cobalt, both from a cost perspective and basically a supply perspective of the metal. So going on to the specifics of these layered metal oxides. So the layered metal oxides are all based structurally and are similar to lithium cobalt oxide. Lithium cobalt oxide was the parent. As we just saw on the previous slide, lithium NMC 111 or 1/3, 1/3, 1/3 is a very commonly utilized layered metal oxide. I would say it was really the first generation of materials after lithium cobalt oxide that were developed, in addition to the NCA. Then basically what the push is, as I said previously, is to go to lower and lower contents of cobalt, because cobalt is a very expensive metal. And also by going to higher and higher nickel contents, you typically increase both the capacity, you increase the capacity of the cell, and also there's a push towards developing these cells, these same cathode materials, to higher potentials. The original lithium cobalt oxide cells were charged to about 4.1 volts versus lithium metal. Current lithium ion batteries for a lot of consumer electronics devices are now being charged up to 4.35 or 4.4 or even 4.45. And we'll go over how some of the developments that enabled this in the future. So, but once again, what we've tried with the push is to go to higher and higher nickel content due to higher capacity and also lower cobalt because it's expensive. And then the other cathode material, which has been utilized for 20 years for high energy systems, is the NCA, which is lithium nickel cobalt aluminum. And the most common NCA material is 80% nickel, 15% cobalt, and 5% aluminum. As I said, you really want to, most all of these layered metal oxides, they need the cobalt to stabilize this layered structure. However, because of this, cobalt is, you need it, but cobalt is both expensive and toxic, and so you really want to limit the cobalt as much as possible. There's really a big interest, as I already said, in pushing these cathodes to higher potential and also higher nickel content. You want to charge these to voltages greater than 4.4 volts. which results in the oxidation reactions of the cathode material, of the electrolyte, and also you end up having transition metal dissolution. So one of the real problems is that these transition metals, in particular manganese and nickel, when you charge the cells to really high potentials, these ions can be solubilized in the electrolyte. What then happens is they're transported, or they are shuttled from the cathode side to the anode side, where they can damage the anode solid electrolyte interface and therefore basically shorten the lifetime of the lithium-ion batteries. And then finally, there's the lithium manganese rich NMC cathodes, which are structurally similar to these layered metal oxides. These have a higher voltage and also higher capacity. However, we're not going to really spend a lot of time going over these materials in my series of presentations because there's a significant amount of problems with these materials, both with voltage fade. These materials have a significant amount of fading of the voltage curves and the voltage of the materials over cycling. And also they have a significant amount of capacity loss, which is also related to this transition metal dissolution on the surface of the cathode. So, these different types of cathode materials, so from going from the 1/3, 1/3, 1/3, 111 nickel, cobalt, manganese, which has very good thermal stability. And so having good thermal stability is a very safe cathode material. You don't have to worry very much about thermal runaway, and the likelihood of cells catching fire or exploding is significantly less. However, the materials have relatively low discharge capacity. As we steadily increase the nickel content from 33% to 60% to 70% to 80% or even 85%, what we can see is there's a steady increase in the overall discharge capacity. However, at the same time, as we increase this overall discharge capacity, we decrease the thermal stability of the electrolyte, which makes the safety of the cells decreased. It increases the likelihood of basically having a catastrophic event such as fire or explosion. And also the increased nickel content also results in a decrease in cycle life. So in addition to loss or decreases in safety, you have decreases in cycle life. And so as we'll go over on the presentation on cathode materials, there's various developments of the electrolyte that are being utilized to try and moderate these safety concerns and also the cycle life concerns. So the next type of cathode material are the lithium manganese spinels. The lithium manganese spinels, the structure of the cathode materials is shown here. Unlike the layered structure, these manganese spinels allow lithium ions intercalation in through the materials, but not in a layered format. These materials have good thermal stability. They also have very good rate capabilities. So in terms of fast charging and fast discharging applications, once again, for high power applications, for things such as power tools, these are widely utilized cathode materials because basically the power or being able to discharge rapidly is more important for these power applications, once again, such as power tools, than in low drain applications such as cell phones and laptops, where you're really more concerned about energy density than you are about power density. However, you do kind of run into problems with these cells upon cycling at moderately elevated temperatures. So if you start getting above 55 degrees centigrade, these are real issues. And this becomes an issue if you're in climates where the temperature is very warm, or if you're with fast charging and fast discharging. Frequently, the cells themselves will warm up just from the resistance of the pack. The internal resistance of the cells can result in heating, which can cause problems. And while the lithium manganese oxide, which we already mentioned a few times, is a very interesting and very good cathode material, it's got relatively low capacity and also relatively low voltage. And so there's been a lot of research in the last 10 to 15 years on what's referred to as the high voltage spinel, which is the lithium nickel manganese oxide. This material has got significantly higher voltage. This is charged to 4.8 or 4.9 volts versus lithium metal. So this is, basically half a volt above where most of your NMCs are, and 0.7 or 0.8 above where the lithium manganese oxide is, which gives us significantly greater energy density. However, the problem with the high voltage spinel is that basically the problem with the reduced capacity upon frequent cycling, especially above 55 degrees centigrade, is even worse. Because at these higher potentials, you get more electrolyte degradation, you get more transition metal dissolution, and you get faster capacity loss of the cells. And so basically the lifetime of these cells is significantly lower with the high voltage spinel than with the standard lithium manganese oxide spinel. So the next type of cathode material are the olivines, which the most by far and away the most frequently investigated and most utilized commercial olivine cathode is lithium iron phosphate. They possess a very nice flat discharge plateau. It's not very sloped, which is good for the most part in terms of very constant voltage. And a moderate discharge capacity at about 150 to 160. But once again, the voltage is pretty low at 4 volts, despite the fact that it's flat. The biggest advantage of lithium iron phosphate is that they're non-toxic. Iron is everywhere. Iron's a very safe, extremely inexpensive metal. They've got relatively little capacity decline through the life of the battery. So while with the nickel, cobalt, aluminum, or the NCAs, or all of the layered metal oxide materials, you get a significant amount of capacity fade or energy fade over time. You really get very, very little capacity fade for these iron phosphate cathodes. They've also got significant safety advantages over the lithium cobalt based cathodes, the lithium cobalt oxides, which makes them really favorable for higher level applications. So for load leveling applications or for grid scale storage applications, coupled with renewable sources such as wind and solar, lithium iron phosphate is probably the leading candidate because of this increased safety, especially with really gigantic packs, modules or what that you might be using for grid scale energy storage. As I said, iron's cheap, readily available, and also environmentally gentle. It's not particularly toxic. And as I think I've already said, these lithium iron phosphate, in addition to really being of a significant interest for grid scale storage and being used in high power devices such as power tools, drills, and saws, they're also pretty widely used in China for the electric bus systems. These are pretty, good for electric buses. And once again, we will continue seeing, I think, lithium iron phosphate in a variety of applications where power density may be more important than energy density, and cost is really king. When you have cost as your most important factor, the lithium iron phosphate is really a very positive cathode material. So on the anode side, within the lithium-ion battery, the graphite is most frequently utilized anode, which is structurally analogous to the petroleum cokes, which were originally developed by Dr. Yoshino. In the structure of the graphite material, you have a layered overall structure of graphite, similar in nature to the layered metal oxides, lithium cobalt oxide or NCA or NCM materials. There's basically a smooth basal plane surface of the graphite materials, and then you've got edges of the graphite, which are basically like the edges of a sheets of a book or pages of a book, where what happens is the lithium ions can intercalate along these edges and into between the sheets of the graphite upon charging of the lithium ion battery. And so this overall lithium ion battery charging mode or charging depiction occurs via a series of what's referred to as staging. And so as you start to integrate lithium or intercalate lithium into the graphite anode, you populate a series of stages of the graphite material where basically there's a couple of different proposed models, the Rudolf Hoffman model or the Dumas-Harold model, where basically you can show that basically either the lithium is all putting into single layers and then more and more layers fill, or you have a few lithiums on each layer and then basically the number of layers all kind of merge together. But either way, what you do is you slowly start to populate some of the sheets of the lithium or some of the sheets of the graphite with the intercalated lithium until you get to the point where all of the sheets of the graphite are filled with the lithium ions. So this can be interpreted once again by various models showing the staging, stage 1 through 4, as we start to lithiate the graphite. And on the charging plots or discharging plots, which just has both of these lithium metal, basically what you can see is you go down, you start to populate these different layers, stage 1L. This first layer has a potential associated with it, which basically is fairly flat. And then as you go to the next stage, stage 2L, where there's more lithium ions intercalated, the voltage of the electrode material drops. And as we keep on going into and then back out of the lithium metal, we can see the stages of the lithium going into and then back out of the lithium metal. And there was, I said, different potentials for these different stages or different phases of the lithiated graphite. So in addition to the staging phases of the graphite upon charging and discharging, one of the critical things that I mentioned earlier in the presentation was that on the first charging cycle of the lithium-ion battery, the electrolyte is unstable to the potentials of the anode material and therefore decompose on the surface of the anode material to generate what's referred to as a solid electrolyte interphase, or SEI. This SEI was proposed originally by Professor Pellet back in 1979, a very long time ago. And it is depicted as shown, it was originally depicted as shown here, which is basically kind of this complicated mosaic of different types of materials containing lithium oxide, lithium fluoride, lithium carbonate, polyolefins, and semicarbonates. And at the time, Professor Pellet proposed that there was a similar surface film on both lithium metal and on graphite or various forms of carbon. And as I said, in a future presentation, we'll go over significant recent investigations in my research group into both the structure and the function of this anode SEI, both on graphite, carbon, lithium metal, and then also silicon, and another very important anode material for modern lithium-ion batteries. But the point of this slide is that on the first charging cycle of the battery, if you compare the first charge and discharge cycle of the battery compared to that of the 5th or 6th or 7th cycle, what you can see is there's a significant difference in the charge and the discharge plot for the first cycle compared to that of the 5th cycle, where they're very, very similar on the 5th cycle. And on the first cycle, what you see is there's an additional significant shoulder here at about 0.6 volts versus lithium metal. And that this shoulder that you observe is consistent with the decomposition of the electrolyte. And so what's happening in this potential range between 0.8 volts and about 0.3 volts is you're seeing a decomposition reaction of the electrolyte. And as the electrolyte decomposes, the surface film, the solid electrolyte interface, is being deposited onto the surface of the graphite. And then by the surface film being deposited onto the surface of the graphite, what it does is it effectively passivates the surface of the graphite, inhibiting further electrolyte decomposition or reduction of the electrolyte on subsequent cycles. And so as I said, the first cycle, we see all these reduction reactions. We don't on the discharge cycle. And once again, on future charge and discharge cycles, we no longer see any significant difference between the charge and the discharge cycles, and we don't see the additional shoulder on the charging cycle consistent with decomposition of electrolyte because the surface of the anode has been passivated. So in terms of other anode materials, so we showed on the, as is shown on this plot, graphite has a relatively low volumetric and gravimetric capacity. However, a whole range of other materials, intermetallic materials, or alloying elements, such as zinc and aluminum and lead, all can have potentially higher gravimetric and volumetric energy densities than graphite. However, the most appealing material is silicon. Silicon, in terms of alloying elements, really has the greatest promise in terms of both the gravimetric energy density and also the volumetric energy density. And so there's been an enormous amount of interest in the research and development on silicon anode materials. However, the biggest problem with the silicon anode material is that silicon has about a 400% volumetric expansion during lithiation and then volumetric contraction during the delithiation process. And so this very large expansion, contraction, creates a lot of problems for the silicon anode. And so research into the development of silicon materials for anodes has shown that basically the performance and the lifetime of silicon anode materials is very dependent upon particle size. And so when you have large particle size silicon, basically what you end up with occurring during these large volumetric expansions and contractions and expansions and contractions is the large particles start to crack. And as you start to crack these materials, you free up more surface. The electrochemical potential of lithiated silicon is similar to that what you observe for lithiated graphite. And so the reduction potential is very strong, and it's below the stability window of the electrolyte. And so as you start to crack these silicon particles and freeing up more and more surface area, what you free up is more and more reactive surface area, which causes more and more electrolyte decomposition, which consumes active lithium. And by consuming the active lithium, the lithium is no longer able to go back and forth between the two electrode materials. So effectively, you lose cycling capacity, and over time, the cell dies. Now, one of the primary ways that researchers have found to get around this problem of terms of silicon cracking and damage to the surface is by going to smaller and smaller particle size. However, the problem with the smaller and smaller particle size is that basically these are complex materials to prepare. They're expensive to prepare. They also have a very large active surface. And so if they have a large amount of surface area, the first charging cycle, a large amount of electrolyte is consumed because one must generate a large quantity of SEI, solid electrolyte interface, to cover all of the surface. And so basically in terms of silicon anode materials, there are a lot of problems with pure silicon anode materials. And so what predominantly has been done now for commercial lithium-ion batteries is you take a graphite anode and then you'll put in a small amount of silicon. So we can put in, say, 10% silicon or maybe 15% silicon. However, since the capacity of silicon is almost 10 times the capacity of graphite, if you add 10% silicon, you can almost increase the capacity of the graphite by 100%. So you can potentially dramatically increase the overall capacity of the anode by taking a primary graphite anode and putting small amounts of silicon in. And this is what's being done commercially. There's a lot of the anode materials, especially for consumer electronics, are now silicon graphite composites, where you have a low amount of silicon. And while you still have some cracking and you have surface area problems of the silicon, the presence of all of the graphite around it kind of basically absorb a lot of these volumetric damages. So next type of anode material are the lithium metal anodes. So within the lithium metal anode, basically the same problems, or many of the same problems, are present that were present when these batteries were originally developed back in the 70s. And that first off, as you cycle the lithium back and forth, you start to generate lithium dendrites or lithium whiskers, as was originally observed by Whittingham. And that these whiskers can grow, connect to the cathode, and then short circuit the cell, which can cause, once again, fire or explosions or damage to the cells. Another problem with lithium metal anodes is you start to cycle, and as you cycle the materials, you start to have small pieces of lithium that basically are broken off away from the bulk lithium metal. And upon doing so, you end up with what's referred to as dead lithium or mossy lithium, where the lithium is no longer able to cycle back and forth between the cathode and the anode. And so basically this is a loss of energy density in the form of these materials. Also, these materials will effectively, this dead lithium will block the lithium ion intercalation from the cathode onto the actual lithium metal and back and forth, which results in a net increase in the polarization or an increased resistance or an increased impedance of the cells. You also end up with significant problems where basically the smooth surface area of lithium starts to kind of change, and you basically have an uneven surface of lithium, which can cause problems. And then finally, you have a lot of different reactions with the electrolyte, which on the surface of lithium metal consume the electrolyte to generate a thicker and thicker anode SEI upon additional cycling. And this thicker SEI also results in an increased cell impedance or resistance of the cell. So some of the other challenges with lithium metal anodes is that the overall plating properties, the ability of lithium metal to be plated and stripped, is very dependent upon a lot of different features and aspects of the cell. So this particular plot demonstrates a change in the current density of the plating of the lithium metal from very low current densities to very high current densities. And what you can see is that when you have very low current densities, you tend to get a very relatively uniform plating on the surface of the metal. However, when you go to these higher current densities, what you see is a whole bunch of very uneven surfaces and a lot of dendritic or mossy lithium being generated on the surface. Now, the problem with this is that basically for a lot of different applications, in particular electric vehicle applications, there is a big push to go to higher and higher charging rates because people want to be able to recharge their cars very rapidly, much like when you would fill your car with additional gasoline, which doesn't take very long. However, if your charging rate is very slow, it decreases the convenience of the vehicle, and it inhibits people from wanting to switch from a gasoline-powered vehicle to an electric-powered vehicle. And this should just demonstrates that with the lithium metal anode, that going to these higher rates can result in even significantly worse problems with the lithium metal anodes, because basically the problem with dendrite growth and the generation of the dendrites is a larger problem at faster charging rates than it is at slowing charger rates. And so this is certainly a large problem associated with the development of lithium metal anions for the next generation of lithium batteries. Another thing that can be shown is that the temperature is very dependent. Or I should say the plating process is also very dependent on temperature. And so we can see that upon changing the temperature from low temperature, or once again, we start to see a lot of different uneven surfaces, to higher temperature where we see a more significantly more even plating with the electrolyte, can once again change the surface morphology of the lithium metal as being plated. And also it can change the overall performance of the electrode. And in addition to the fact that there's a lot of interest in high rate charging for electric vehicles, another significant issue with electric vehicles is charging the batteries at very low temperature. Current lithium ion batteries already have problems with charging at low temperatures at 0 degrees centigrade or below because of the kinetics of the lithium ion transport through the interfacial films. And once again, what we generate with the lithium metal surface is you generate a much more uneven plating of lithium, more presence of dendrites when the materials are plated at low temperature than when the materials are plated at high temperature. Now, what we can see is when we change the electrolyte, and vinylene carbonate, VC, is an example of an electrolyte additive. And in this case, so if we make a small modification to the electrolyte by converting from an electrolyte which does not contain vinylene carbonate to an electrolyte which does contain vinylene carbonate, once again, we can overall change the plating performance of the lithium metal onto the anode surfaces. And this is really one of the aspects that scientists are currently utilizing to try and improve the overall performance of lithium metal anodes, is by modifying the electrolyte formulations. And this is something we'll see much more about in future presentations. So now the final section here is really going back over some of the problems with current lithium-ion batteries. And so, as many of you know, as I'm sure all of you have currently in your possession lithium-ion batteries, either in your cell phone or on your laptop computer. In fact, you're probably utilizing a lithium-ion battery to watch this presentation currently, or very well might be. And basically, you've realized that with the lithium-ion battery that powers your laptop computer or powers your cell phone, that the amount of energy that the battery stores 1 year after you purchased it wasn't quite as good as it was when the battery was brand new. And after 2 years, it's even worse. And after 3 years, it's even worse. And so one of the things that we study in my laboratory is that process, is the aging of lithium-ion batteries. And you know, why does the performance of lithium-ion batteries decrease over time? And so basically, the main reason is you have a loss of lithium due to the reaction of the electrolyte with active material, which could be either the cathode surface or the anode surface or some combination of this. And basically, you have this continuous formation of the solid electrolyte interface, which results in this gradual loss of lithium, and your lithium is not allowed to move back and forth. And so once again, you know, you start off and you really think it's great, and a few years later, the battery is not as good. And so, you know, why do these lithium-ion batteries not last forever? Well, let's look at all of the different components of the lithium-ion battery. So the current collectors, so I haven't really mentioned the current collectors at all before, but in a lithium-ion battery, you have anode material, as I said already, which is typically graphite, a cathode material, which is typically a lithiated metal oxide. In addition to that, these electrode materials are coated onto current collectors to actually build the cells, to build the batteries. The current collectors on the anode side are copper metal, and on the cathode side are aluminum metal. So in terms of trying to make these batteries last a long time, and also in terms of getting the batteries have as much energy density as possible, and you're always trying to do both of those things, or I should say generally trying to do both of those things, you want to try and make these current collectors as thin as possible, but they also need to be strong as possible to last a long time, to allow the electrons to flow along the length of the current collector, because once again, as a current collector, this is your electrical conduit from the electrode to the circuitry that's connected to the battery, that's allowing the battery to power things. In general, the copper current collector on the anode is pretty good. There really aren't a lot of problems with it. Copper is the biggest problem with it is that copper is relatively expensive. So this adds a lot of cost to the battery. So if one could find an electrode material other than copper for the anode current collector, that would certainly be preferable. On the cathode side, the current collector is typically aluminum, which once again is less expensive than the copper, which is an advantage, and also works pretty well. However, one of the biggest problems with the aluminum current collector is that under certain types of conditions, especially at really high voltages, you can get corrosion problems with the aluminum current collector. And so the aluminum current collector can get damaged, as I said, especially when you go into high voltage cells, and this can be problematic. I also haven't really mentioned the separator. So all lithium-ion batteries, in addition to the liquid electrolyte that allows the lithium ions to go back and forth, There's also a plastic polyolefin separator that separates the two electrodes from each other and basically prevents the two electrodes from coming in direct contact, which would result in an electrical short of the system. So, on the cathode side, what you're trying to do is have more lithium ions per unit volume. You're wanting to go to higher voltage, increased density of the electrodes. This is something that I haven't mentioned much, but once again, how well you pack and how thick these electrodes are corresponds to basically how much lithium ion can be stored on the electrode material. You generally want to go to very, very thick electrodes. However, our current coating processes, our current commercial coating processes only allow certain thicknesses of the electrodes to be coated. And at the same time, if you go to too thick of electrode, the lithium ions cannot basically migrate all the way down to the lower portions of the electrodes very easily. And so basically electrode thickness is one of the optimization parameters that's really been worked on significantly, as I mentioned earlier with the Panasonic cells. One thing that has been able to do is go to thicker electrodes. However, there's a limitation on how thick the electrodes can be. And basically what you want to do is pack more cathode into the smaller volume of the battery. And on the anode side, you want more lithiums per unit volume, low voltage, which it already has, increased density and thick electrodes once again, and we want to use less of the battery volume for the anode. So, what are these problems with the current lithium-ion batteries? So the anode material, the negative electrode, carbon anodes, it's relatively low capacity. Ideally what we want to do is replace carbon with improved alloys such as silicon or even lithium metal that allows higher coulombic efficiency, good power capability, and low irreversible capacity. The irreversible capacity is typically associated with SEI formation, and also low cost. And so currently what's probably the most frequently utilized method for doing this in commercial cells is putting some silicon in with the carbon and with the graphite, which increases the capacity of the material and can do so significantly, although usually at a cost to cycle life. The next one is the negative electrode electrolyte interface. So this one I've already mentioned. This is the solid electrolyte interface. Basically, we have low coulombic efficiency with the alloy anodes, such as silicon, which is caused by this solid electrolyte interface being formed and growing on subsequent cycles. So if you have an anode material, such as silicon, where you have a large volumetric change and you have a significant surface area changes, you end up having a lot of electrolyte consumption in the form of this solid electrolyte interface with additional cycling of the cells. And how can we get around this problem? Well, we can utilize improved coatings of the surface, functional binders, which once again I didn't mention, but all of these electrode materials, either cathode or anode, which are the active materials of the electrodes, they also contain polymer binders, which basically hold the laminate together, hold the entire cathode material together. Also, which we'll see in some of my presentations over the next few presentations, are electrolyte additives. So you can use electrolyte additives such as the vinylene carbonate that I mentioned a few slides before, and these electrolyte additives can modify the structure of the solid electrolyte interface to generate a better electrode material, or a better interface, or a more stable interface. So on the positive side, basically you can replace the cathode material with one that has higher coulombic efficiency, good power capability, and low irreversible capacity. Really with this, you have cathode, especially at high potentials, the cathode can oxidize the electrolyte, which results in transition metal dissolution. The transition metals can be transported to the anode side, damage the solid electrolyte interface, and cause problems. And once again, there's a push towards increasing the specific capacity of the cathode material and inhibiting these decomposition reactions of the electrolyte, or what you consider kind of a corrosion, where the electrolyte reactions on the cathode cause a detrimental etching to the surface of these cathode materials. So the positive electrolyte interface, once again, so more or less what I said, we have low coulombic efficiencies. We need to improve the coating of the cathode materials. And so one of the ways that scientists have been doing this is they've been taking their standard cathode materials, such as lithium cobalt oxide or nickel cobalt aluminum, NCA or NCM, and they've been coating these with more inert materials, such as alumina, Al2O3, or titania, or things. If you can put these surface coatings, or aluminum fluoride, you can put these surface coatings onto the surface of the cathode, which still allow lithium ions to intercalate through them, but inhibit the reactions of the electrolyte with the surface of the cathode materials at high potential. And once again, another mechanism to inhibit these electrolyte reactions with the cathode surface is the development of novel electrolyte additives, which can either selectively, sacrificially decompose on the surface to generate passivation layers, or inherently inhibit these detrimental oxidation reactions. So the separator, in general, I would say lithium-ion battery separators are fairly good. Most of them currently, they're a little bit on the expensive side, considering that most of them are polyolefins, polypropylene or polyethylene. And basically the problems you have here is penetration with conductive particles, such as the lithium dendrites. And how can you stop this? Basically, you can make more rigid separators, or you can improve the coatings of the separators, which do not impede the ion flux, but can improve the overall penetration strength. And so one of the ways that people have been doing this is they've been taking standard polyolefin, polypropylene based separators, and then coating the separators with something such, once again, as alumina, which basically can make a more stable surface, and also make the separators themselves more mechanically stable. The metal current collectors. So these, as I said, these are solid metal foils. They add a significant amount of cost and take away energy. They're basically inert in the system, but they have to be thick enough to provide adequate electrical and thermal conductance. They also have to allow enough mechanical strength to basically build the cell. So like with cylindrically wound cell, they have to have enough mechanical strength to hold the integrity of the electrode together. Some of the ways that people are looking at improving the performance of this is perforated or expanded metal collectors, which are already in use in primary batteries. But once again, if you go to something that's too perforated, or as basically you could lose mechanical strength, which could cause you problems with the overall manufacturing of the cells. And so finally, we'll just quickly summarize what the future is in terms of beyond lithium metal. And so, or lithium-ion batteries. And so this is where lithium-ion batteries are for us today in terms of basically their volumetric or gravimetric energy density. We'll say we're in this region here. And perhaps there's a little bit of an expansion out towards this region with further developments and further advances for lithium-ion batteries. However, in terms of the next generation of lithium-ion battery or lithium or battery materials, we'll say, we can certainly go to much higher gravimetric energy densities by going to lithium sulfur or organic batteries. There's also the possibility of magnesium or zinc or calcium batteries, divalent systems. However, there's a lot of challenges with divalent ions such as magnesium and calcium, because all of the lithium ion technology is based on intercalation compounds, or most of it. Both the graphite anode and the lithium metal oxide cathodes are based on intercalation compounds. Monovalent ions such as lithium intercalate pretty well. In addition, lithium is a very small ion, so this combination of a monovalent ion and a small ion make it very good at intercalation. However, if you go to larger ions such as calcium or divalent ions like magnesium and calcium, basically the intercalation is a much bigger challenge because effectively these ions stick to the surfaces better and don't intercalate as well. And of course, there's also the lithium oxygen battery and then solid state with lithium metal ions, which are really the drivers of what a lot of the future research is going towards which is all solid state batteries and or these lithium oxygen batteries. And so finally, just in summary in terms of the lithium ion battery and what the next few presentations will be going over. The next presentation will be focused on the electrolyte, which once again in standard lithium ion batteries is lithium hexafluorophosphate, LiPF6, dissolved in a mixture of carbonate solvents, which predominantly all contain ethylene carbonate, EC, and most of these electrolytes also contain some form of additives, and the additives are incorporated into the electrolyte to generate a more stable surface film on either the anode or on the cathode. And as we've seen today, typical anode materials in commercial lithium-ion batteries are graphite, although there's a big push to move away from graphite towards either silicon or lithium metal, because graphite has relatively low capacity, and both silicon and lithium metal anodes have significantly higher capacity, and therefore would generate lithium batteries with greater energy density. On the cathode side, the original developed cathode material of lithium-ion batteries was lithium cobalt oxide, and I would say most lithium-ion batteries contain very similar cathode materials of the NCA materials, or NMC, which is nickel cobalt manganese or nickel cobalt aluminum. And in both of those cathode materials, it's still the layered metal oxide. There's a big push to go to higher capacity cathode material, higher voltage cathode materials, but those result in negative oxidation reactions of the electrolyte. And we'll see about those reactions of the cathode with the electrolyte, especially at high voltage in the future, and also the reactions of the electrolyte with the anode surface in the future also. And with that, I'd like to conclude my talk. Oh, man. Stop sharing. And thank you again for listening to the presentation. And I will look forward to giving the next few presentations. Thank you very much.